Discovering the SSRF vulnerabilities. We will start by opening Burp Suite, turning off Intercept if it is enabled, and opening the embedded browser. Next, we will access the login page at Group Office. We will enter the provided credentials and click Next. When assessing a new application, we should always spend some time exploring the application to get a sense for what the application does and any interesting functionality. In this case, we can add portlets to the Start page by clicking the Add button. We'll click News on the resulting pop-up window. After the pop-up window closes, we have a news frame added to the Start page. Let's try configuring this new portlet by clicking on the gear in the top right corner of the frame. The application will open a new window titled RSS Feeds. This new window includes a table with 3 columns: Title, URL, and Summary. The URL field should stand out based on what we've learned about SSRF vulnerabilities and suggestive parameters in this topic. If the application does send a request to the URL, we'll need a way to verify it. Let's use the Apache server on our Kali VM and submit our IP address in the URL field. First, we'll use systemctl to restart our Apache service. Now that we have Apache running, we'll return to our browser and click Add. We'll then enter Test in the title field and our Kali IP address in the URL field. Since we're not sure what the summary checkbox does, we'll leave it unchecked for now. After clicking Save, the window closes and we're back on the Start page with Test listed under News. Let's use Tail to check our Apache access log for any new connections. Excellent. The Apache server on our Kali VM received a request. According to the user agent field, the application used curl to send the request. Curl supports multiple URL schemes, so we may be able to access local files with the SSRF if the application does not perform any input validation on the URL value we submit. Let's review the requests we've sent in Burp Suite. The Group Office site generates some requests automatically, so we may need to scroll through our history to find the requests that start with URIs like the following. This request seems particularly interesting because of the word proxy in the query string. Let's test if this is the request that generated the forged request to our Kali VM. We'll right-click on that request and send it to Repeater. Next, we'll click on the Repeater tab. We want to make sure this is the request that generates the forged request, so let's update the feed parameter by appending /repeater to our IP address. This will give us a unique value to check for in our Apache logs when we verify if this endpoint generates the request to our server. Let's click Send. The response from Group Office seems to include an HTTP 404 response page from our Kali VM. Let's check our Apache access log and verify we received the forged request. Excellent. We have a request to repeater in our access log, and Group Office seems to render the HTTP 404 response page. We may be able to use this technique to access the results of the SSRF vulnerability. Before we move on to exploitation, let's continue to explore the application. We can find another interesting feature in the My Account page, which we can access by clicking the silhouette in the upper right-hand corner. We'll then click My Account on the pop-up list and then click Account. On the resulting page, we can click on the silhouette in the upper left-hand corner to get yet another list of options. The From URL option seems interesting. Let's click on that. This new dialog window presents us with a single field for a URL. Depending on how the application handles this data, we might have another SSRF vulnerability. If the application requests the image and saves it, we can likely exploit it for SSRF. However, if the application only uses the value we submit to embed images via an image tag, it will not be exploitable. Let's try it out by submitting our IP address appended with From URL so we can easily identify a request in our access logs. After clicking OK, the user profile picture changed from a silhouette to a gray circle, so something happened. Let's check our access log for any new requests. It seems we have found another SSRF vulnerability. Since we're updating the user's profile picture, we should be able to retrieve the results of the SSRF vulnerability. However, we just requested a page from our Kali VM that does not exist. Let's check the HTTP History tab in Burp Suite to find the request that triggers the SSRF. We may have to scroll through auto-generated requests to find the GET request to API upload.php. This request includes the URL we submitted. Let's send this request to repeater so we can resend it later. Interestingly, the response to our request includes a blob ID, and the subsequent request is to API-thumb.php with the blob value included. The server responded to API-thumb.php with an HTTP 500 error. Perhaps this is because our URL didn't return anything. We'll send this request to repeater as well. Now let's create a valid page and retry this attack. We'll echo "it worked" into a file and move the file to our Apache server's web root. Now that we have a simple HTML file, Let's go back to the Repeater tab with the request to API upload. We'll update the URL parameter to use our new file. The response includes a new blob ID value. Let's copy that value and switch to the Repeater tab with the request to API-thumb.php. We'll replace the old blob ID value with the new one and click Send. Unfortunately, the server responded with an HTTP 500 internal server error. The error message indicates the application treats the file we requested as an image. We created a simple HTML file, which will lack the metadata an image file contains. It may be more difficult to retrieve the results from this second SSRF vulnerability. Still, we have two different attack vectors. In the next section, we'll attempt to exploit both of them. Exploiting the SSRF vulnerabilities. Let's return to the first SSRF vulnerability we identified in the RSS feed functionality. From the user agent header, we know that the application uses curl to send the request. We should be able to access other URL schemes since we control the entire URL value. We will go back to our tab in Repeater. Let's try to access a file on the application's OS. We'll update the feed parameter to file etc password, and then click Send. Unfortunately, the application returned an empty response. Perhaps the application includes server-side logic to block the file scheme or perform some validation on the file contents before displaying it. We're left with a bit of a conundrum. We have one SSRF vulnerability that renders the results but seems to block the file scheme. We have another SSRF vulnerability that we haven't tested for the file scheme, but we cannot retrieve the results. Let's explore the application some more. Maybe we'll find another feature that can help us. Let's start by clicking on the address book. Interestingly, the users in the address book include profile pictures. Two of the pictures are gray circles, like the one shown for our admin user when we updated the profile with an invalid image. If we click on John Smith and then click the profile picture, our browser will open a new tab. Notice that this new URL includes a blob in the query string. We should recall that our previous attempt at an SSRF attack against API upload returned a blob ID value. Let's return to that request in Repeater and retrieve the blob ID value. We'll update the blob value in the URL and reload the page. Nice! We retrieved the HTML file we loaded with the second SSRF vulnerability. Let's send this request to Repeater so we can reuse it later. Next, let's determine if we can access local file contents. In Repeater with the request to API upload, we'll change the URL parameter to file etc password and click Send. We received an HTTP 201 created response with a new blob ID value. Let's copy the value, switch tabs in Repeater to the API download.php request, and replace the blob value. We'll then send the request to the server. Excellent! By exploiting the SSRF vulnerability in the image upload to get a blob ID value, and using the download URL with that value, we can access files from the underlying server. As this example illustrates, not all attacks are straightforward. Sometimes we must use other functionality within the application to access the results of our attack. Once we can read files from the server, we can search for configuration files or credentials that we can use for other attacks against the application or server. Exploiting static file IDOR. Let's review an example of insecure direct object referencing within the IDOR sandbox. When we visit the landing page for our IDOR sandbox application, we will notice a series of buttons that direct us to their corresponding topic pages. We can start by clicking File-Based IDOR. We will be redirected to this URI. Next, let's closely examine the data rendered and displayed on this page. The output shows exfiltrated information from a text file on the target web server. Based on what we learned regarding file-based IDOR, let's attempt to manipulate the f=1.txt value and increment it once. After submitting our new query string, we'll receive different output. Our suspicions of being able to exfiltrate information by incrementing this text file object referencing worked very well. We supplied the f parameter with the value of 2.txt and were presented with different output than before. This time, we managed to exfiltrate the full name of an individual, where they are from, and whether or not they are a registered organ donor. In the coming section, we will discuss the exploitation of ID-based IDOR. Exploiting ID-based IDOR. Let's now examine database object referencing, or ID-based IDOR. On the Sandbox landing page, we'll click ID-based IDOR. This redirects us to this URI. The URI seems to contain a numerical customer ID. This is highly indicative of a classic IDOR finding. Before performing any iteration, Let's more closely inspect the output rendered in the web browser from the result of a customer ID value of 1. Let's note the types of information retrieved from the database before we move forward by incrementing customer ID to 2. We can confirm that this is a case of IDOR by taking note of the output rendered in the web browser as a result of our incremented value. Essentially, we can iterate through the database table directly from an insecure endpoint to retrieve the same type of information belonging to a different customer. We'll note we retrieved the user ID, handle, name, location, and the customer's member status. Accessing this type of information by incrementing a database value in the query string indicates the presence of database object referencing IDOR. In the coming section, we will continue with our exploitation of IDOR by discussing UIDs in more detail. Exploiting more complex IDOR. To begin, we will cover the exploitation of user IDOR from an authenticated perspective. Let's log in as the user Harb. Once logged in, we will be notified of a successful login attempt. We will also be redirected to this URI, which shows the output corresponding to the user Harb. The output includes the UID, name, handle, geographical location, and member status of our signed-in user, Harb. Next, let's attempt to retrieve information about other users. We can even demonstrate exfiltrating user data with unknown UIDs. Our current UID consists of 5 sequential characters. This adds a semblance of security for the registered member. However, the premise behind this attack is to brute force potential UIDs and iterate programmatically through thousands of possibilities. In order to brute force the UIDs, we'll iterate through the options 100,000 times using a word list from seclists. If we fuzz all of these requests, we'll receive a lot of responses to review. Let's send a request with curl so that we can establish a baseline response size. We'll use this response size to filter our wfuzz results. The -s argument instructs curl to not display a progress bar since we are only interested in the response size. Finally, we can specify the -w size download argument value combination, directing curl to print the response size in the terminal output. Our output came back as 0 bytes. This is because we did not specify a valid session ID when we executed our curl request. In web application assessments, we will often need to do both unauthenticated and authenticated fuzzing to retrieve accurate results. This means we need to include a valid session ID in our wfuzz command. To retrieve this session ID, we need to enable intercept and capture a request from the login URI. Capturing this request provides us with a cookie value. We can use curl again, this time with the session ID, and attempt to gain an erroneous response size from an authenticated perspective. The next curl command is only slightly different than before. We'll add the header argument for an authenticated request, and also include a random UID value to gather a known erroneous response size. The response size for a logged-in session's erroneous output is 2873 bytes. We'll make sure to exclude this value in our upcoming fuzzing attempts. Let's begin fuzzing. Within wfuzz, we can use the -c argument to denote that we would like color output. Next, -z acts as our file input method. We'll specify file followed by our word list. Next, we'll exclude any 404 responses. To exclude our erroneous bytes, we'll provide the HH argument. We also need to provide a header containing a cookie value. This can be done using the -h argument followed by the cookie value we previously collected. And finally, our fuzzing endpoint. We have successfully managed to retrieve other users' UID values. We could exfiltrate information about these users by simply providing these values in place of our valid UID. Let's give it a try. We'll point our browser to a new URI using a UID collected from our fuzzing. We have successfully exfiltrated the name, handle, location, and member status for the user McLovin. In the next learning unit, we will cover an IDOR case study for OpenEMR. Discovery of the IDOR vulnerability. We'll begin our discovery phase by browsing the web application and assessing any potential parameters or functionality that stand out based upon what we've learned in this topic. Let's first ensure Burp Suite is started and that the Intercept button is turned off for now. We'll start discovery by launching our web browser and pointing it to OpenEMR. We will log in as a low-privileged user called LowPriv. After a few moments, we will be presented with the dashboard interface for OpenEMR. Our user's name is shown in the upper right corner of the page, indicating we've successfully logged in as the low-privileged user Nancy Jones. Whenever we explore new web applications, we should take the time to manually peruse the app to better understand how it functions and how we might discover vulnerabilities. Because this is such a large medical platform, there are many different buttons, tabs, pages, and forms we can inspect. To start, we'll notice directly on the landing page that we are presented with two separate tabs, Calendar and Message Center. After clicking Message Center, we will be shown a table with one entry. It seems that confidential information pertaining to patients or staff will appear here. The table consists of a few buttons we can click on, including Messages, Reminders, and Recalls. We can also add a message as our current user. For now, let's inspect the message sent from Nancy to Stan. It's important to note that we must allow each and every request sent from this application to resolve in full. The application has the potential to hang while processing background information. Once we have confirmed our previous request to the message center is complete, we'll continue and click on Stan's name. This page allows us to reply and offers other options. We might be able to view the complete message by using the Print Message option. Before attempting this, let's return to Burp Suite and turn on Intercept. With the Intercept functionality enabled, we can return to the patient messages and click Print Message. Inside the body of our captured request, we will right-click and select Send to Repeater. Now we will click Send. As demonstrated, we have sent the request and we can now more closely observe both the requested URI and the response containing the full message. It certainly seems that the node ID parameter with the value 11 sent in the request is very similar to the parameters we encountered in our IDOR sandbox. Based on the knowledge we've gathered, we can guess an IDOR vulnerability may be lurking here. With our discovery phase complete, we can begin exfiltrating data in the next section. Exploiting the IDOR vulnerability. When exploiting this vulnerability, our primary goal is to exfiltrate the maximum amount of data possible. Now that we have discovered a vulnerable endpoint potentially susceptible to a form of IDOR, let's test our suspicions about using Node ID for further data exfiltration. We can reasonably determine we've encountered an ID-based IDOR finding. We'll disable Burp Suite's Intercept feature from this point forward. Let's take the request from the previous section, located in our repeater, and load the endpoint into our browser to observe the output. We've received the complete output from a message sent by a help desk staff member, including sensitive information about upcoming new patients. This information does not appear to be immediately helpful with further system compromise. However, if we were to iterate and decrement the value of Node ID, we might stumble across more valuable information. In this instance, we were a bit luckier. If we were to penetrate the security mechanisms of this system, we would essentially have the IP addresses of neighboring machines on a private IP range, potentially enabling us to move laterally on the network. We could continue this process of incrementing and decrementing the vulnerable endpoint to potentially retrieve even more valuable information for target compromise. This demonstrates an extremely severe vulnerability. By compromising medical data, we've observed a critically sensitive information leak between a doctor and their patients. Basic host enumeration and OS detection. Let's start by enumerating the server using Nmap. Though most web applications run on the standard HTTP or HTTPS ports, they can run on any port or even multiple ports. For example, a web application might serve HTML content on port 80, which calls web services on port 8080. If we focus only on port 80 in this case, we might miss important functionality. When conducting web application assessments, we need to strike a balance between the speed and coverage of automated tools. Running a quick scan with broad coverage will often provide us useful, actionable information. A longer, more comprehensive scan can be useful to ensure we don't miss anything, but we can often run these longer scans in the background while we perform manual testing. With that in mind, we'll start with a basic Nmap scan of our target machine. Since we're not specifying any options about what to scan, Nmap will scan the 1,000 most commonly used TCP ports. This option provides us with good coverage of the ports that web applications typically use. Our Nmap scan identified 2 open ports. Servers usually run HTTP on port 80, and Remote Desktop Protocol usually runs on port 3389. We could be dealing with a Windows host. Nmap includes an operating system detection feature. Let's run Nmap again with the -o argument to enable this feature, and -pn to disable ping probes because we know the host is up. Unlike the previous scan, we'll need to run this command with sudo. Nmap's output warns us that the results may be unreliable and the server could be AV-Tech embedded or Windows. Because we're dealing with a web application, we are more likely dealing with a Microsoft OS than an AV-Tech Room Alert environmental monitor. However, we'll have to keep multiple operating systems in mind as we develop any exploits until we can definitively determine the correct OS. Now that we have some basic, albeit incomplete, information about the host, we will turn our attention to the web application and perform content discovery. Content discovery. Let's start by examining the web application to get a sense of its functionality. If we know the application's intended use, we can focus on areas that might include vulnerabilities or exploitable misconfigurations. Our first step will be exploring the web application as a normal user. We'll do this with a browser proxied through Burp Suite so we can capture all requests and responses for later inspection. Let's start Burp Suite, disable Intercept, open the embedded Chromium browser, and browse to the challenge machine. The home page indicates we're dealing with a pizzeria. Before we continue, let's take a moment to review the HTTP History tab in Burp Suite. Web applications will often load resources from multiple domains. These requests can clutter up Burp Suite if we don't filter them out. As we suspected, the web application loads font files from an external domain. We have several ways to hide or exclude these external requests using Burp Suite's scope settings. When we add a URL to scope, we want to select the base URL so Burp treats all traffic to the site as in scope. Let's scroll to the first URL request, right-click on it, and select Add to Scope. We'll receive a pop-up window asking us if we want to stop sending out-of-scope requests to the history or other burp tools. We may want to inspect these requests later, so we'll click No for now. We can still temporarily remove these items from the HTTP History tab by setting a filter. To do this, we'll click on the filter bar above the HTTP History table, which triggers a pop-up filter settings window. We'll click the checkbox for Show Only in-scope items and then click Apply. The HTTP History table will now filter out the 2 out-of-scope requests. As with any feature that limits or excludes data, we need to be careful not to exclude too many things, which might cause us to miss a vulnerability. By using a filter to remove external requests from HTTP History, Burp Suite still captures the external requests, but does not display them until we remove the filter. We can always remove the filter later if we need to review that HTTP traffic. Let's continue exploring the web application. If we click on the links in the page's header, our browser scrolls to the relevant section of the page without loading a new URL. The newsletter and contact sections include fields that seemingly allow us to submit data to the server. Let's submit values in these fields so we have examples in Burp Suite of what requests the application sends. We'll start with the newsletter section. We'll type web-200 at test.local in the email field and then click Subscribe. The web page does not reload and displays the message, "Thanks for subscribing." Let's check the HTTP History tab in Burp Suite. Our browser sent a post request to newsletter, and the application responded with a short JSON body. Let's right-click on the post request and select Send to Repeater from the context menu so we can easily return to it if necessary. Let's return to our browser and click on Contact. We'll fill out the name, email, and message fields. The values we use while testing functionality during a web application assessment don't matter very much. However, we will often find it useful to use values that will be easy to find or identify if the application stores them or reuses them in some way. We'll type web-200 for the name, web-200 at test.local in the email field, and assembling the pieces in the message field. Finally, we'll click Send Message. Once again, the page updates without reloading. Checking the HTTP history in Burp Suite, we find a post request to contact. Let's right-click on the request and select Send to Repeater so we have a copy we can easily return to if necessary. Now that we've explored all the functionality we can find on the home page, let's use another tool to search for more pages. Let's run GoBuster in directory file enumeration mode with the dir command. We'll specify our target URL with -u and a word list with -w. GoBuster found 8 potential endpoints, but only one of them returned an HTTP 200 OK response. However, we can still infer useful information from the non-200 responses. For example, admin returned an HTTP 302 found response and redirected to login. This means admin is probably a valid endpoint that requires authentication. The contact and newsletter endpoints returned HTTP 405 method not allowed responses. When we were exploring the web page in our browser, we sent post requests to these endpoints. GoBuster sends GET requests by default, so these responses seem normal. Let's check the login page in our browser. The login page allows us to log in with credentials or an API key. Unfortunately, we do not have either right now. Next, let's check the error page for any useful information. The error page doesn't contain much. However, the message, "You are seeing this as a fallback," suggests this might be a default error page. Because the page title is White Label Error Page, let's try Googling that. The top search results indicate that we might have found a default error page for Spring Boot, a framework for running standalone Java applications. Knowing the application's programming language and frameworks may be useful once we're ready to exploit it. The last result from the GoBuster scan is for specials, returning an HTTP 400 bad request. Specials is one of the links in the header of the home page, but none of those links reference other pages or endpoints. Burp Suite automatically builds a sitemap based on all proxied traffic. Let's take a moment to review the sitemap in Burp Suite by clicking on Target and then clicking on Sitemap. After expanding the sitemap, we find that our browser did make a GET request to winter.html and received an HTTP 200 OK response. In contrast, GoBuster received an HTTP 400 response when it sent a GET request to the same endpoint without any query string values. It is also interesting that our browser sent winter.html in a query string value rather than as part of the base URL. In fact, none of the pages we've interacted with have included a .html extension. Let's send this request to Repeater so we can manually investigate it further in the next learning unit. Finding a directory traversal. So far, we identified the winter.html endpoint for further testing and sent the original request to Repeater. Let's go to Repeater and click Send so we have a baseline request and response. Since the menu parameter value references a file, let's try modifying it to a different value and checking how the application responds. We'll change winter.html to web-200.html, then click Send. The server responded with an empty HTTP 200 OK. We'll need to do some more testing here. Because it seems like the application might be retrieving a file based on the parameter value, Let's try accessing a file on the server using a directory traversal attack. We could run a tool like wfuzz with a word list, but let's try some targeted attacks first. If our manual testing fails, we can always use word lists to expand our testing in case we missed something or misinterpreted results. First, let's consider what we learned from our Nmap scans during enumeration to help guide our manual testing. Our Nmap scans found TCP port 3389 open, but identified the OS as an embedded AV Tech device or Windows. Since we're assessing a web application, we are likely dealing with some version of Windows. If the server is a version of Windows, then the win.ini file may be present in the Windows directory. Some versions of Windows don't include this file, but we should still check for it. We'll need to add several instances of .. to our payload to traverse back to the base directory of the server. In Repeater, let's change web200.html and click Send. Excellent. The server response includes what appears to be the contents of win.ini. We have verified the existence of a directory traversal vulnerability. In the next section, we'll focus on exploiting this vulnerability. Exploiting a directory traversal. Before we continue exploiting the application, let's recap what we've discovered so far. We've identified a directory traversal vulnerability in a Java application using Spring and running on a Windows server. Perhaps we can use the directory traversal to access the application's configuration files. According to the documentation, Spring applications load properties from application.properties files in 4 locations: a config subdirectory of the current directory, a class path config package, and the class path root. In Java, class path refers to a location that contains dependencies outside of the standard Java files. This could be located anywhere on the server, so let's start with our focus on the first 2 locations. wfuzz can fuzz multiple payloads, which means we can make 2 small word lists. One will contain path traversal strings. In the previous section, 7 instances of .. were enough to traverse back to the root of the C drive. With that in mind, let's create paths.txt with a list of traversal strings, starting with 1 .. and building up to a total of 7. Next, let's build a list of file names. Since the file could be in the current directory or in a config subdirectory, we'll add config to our new file. When we run wfuzz, it will combine the contents of the 2 files together, matching each payload in the first file with each payload in the second file. In other words, because paths.txt has 7 payloads, and files.txt has 4, wfuzz should send 28 requests. Let's try running wfuzz with our word lists. We need to specify them in order of use, so we'll set -w paths.txt and then -w files.txt. We'll also set hh0 to filter out any empty responses. Finally, we'll add our URL in the query string, marking 2 places to fuzz. wfuzz found 1 response with a non-zero response size. Let's use curl with the combined payload to get the full response. Nice. Our directory traversal attack worked, and we now have access to the application.properties file. Based on our previous Nmap scans, the application's database isn't externally accessible. Perhaps we can use the admin portal key value on the login page we found earlier. Let's return to our browser and go to Login. We'll change the login method to API key, enter the value from application.properties in the API key field, and click Login. Excellent. We've successfully logged in to the admin section. Now that we have access to another section of the web application, we'll need to enumerate any new pages and functionality. The admin page will display the contents of local.txt. We can submit this value on the labs page to gain credit for completing the authentication bypass portion of this challenge machine. In the next learning unit, we will focus on discovering and exploiting a vulnerability in the authenticated section of the application to obtain remote code execution. Remote code execution. Now that we have access to the admin section, we have access to view and delete user-submitted messages and newsletter subscriptions. Let's click on the Delete button for our test message and test subscription so we have sample requests in Burp Suite for each function. When the web application prompts us if we're sure we want to delete, we'll click OK each time. Next, we'll go to the HTTP History tab in Burp Suite and send the post request to Repeater before continuing to the next section. Finding SQL injection. Because unauthenticated users can submit messages or subscribe to the newsletter and the admin page includes their results, the application likely uses a database. Let's inspect the request that deleted a message. Our browser sent a post request to admin message delete with a query string of ID equals 4. The request does not include a post body, so the application must be using the value in the query string. Let's try testing the ID parameter in the query string for SQL injection. If the application is using this value to construct a SQL query, it might end up with something like delete from some table where some ID equals 4. Let's click Send to collect a baseline response. The application responded with an HTTP 302, redirecting back to admin. Let's try adding a single quote to the ID value. Remember, numeric fields do not need to be inside quotes in SQL. If the application is vulnerable to SQL and constructs a query with our input, adding a single quote would likely cause a syntax error. Let's add a single quote and then click Send. The application responded with an HTTP 500 internal server error. We might have discovered a SQL injection vulnerability. Because we're trying to delete a message, the application is likely either updating one or more fields in the record or deleting the record entirely. In either case, a union payload won't work since the application doesn't display the results of the query. If the database supports them, stack queries can be extremely useful when injecting into delete or update statements. Not all databases support stacked queries, but PostgreSQL and Microsoft SQL Server typically support them. The application.properties file we found with our directory traversal attack included a database section and which driver the application uses. The application.properties file lists a driver for Microsoft SQL Server. This means stacked queries should work. We can verify this with a simple stacked query, such as selecting the SQL Server version. In Repeater, let's update the ID parameter to the following. We'll need to encode the space as a plus sign before we click Send. The application responded with an HTTP 302 redirecting back to admin. The application responds the same way to a valid request, but we don't know if our stacked query actually worked. We can try to insert a record to determine if the database executed our stacked query. However, we don't know the table names. If we assume the web page contents include everything in the corresponding tables, then the newsletter subscriptions table would have ID and email fields. If the ID field auto-increments, we wouldn't need to include a value for it and an insert statement, thus simplifying our payload. At this point, we're making several assumptions or guesses. We also don't know the table name we're targeting. However, we can still do some fuzzing based on our educated guesses. Let's start by making a short word list of what the table name might be. Now that we have our word list, let's plan our payload. We need to insert an email address into an unknown table. The page responds with an HTTP 302 on a valid request, and since we're stacking queries, we may not know which payload was successful. To account for this, let's insert the table name in the email column instead of a static value. The application should display the table name on the admin page in the list of subscriptions if the application processes our payload. We'll use wfuzz with two payloads again. This is our base SQL payload. We want the same value placed as both the table name and the email value. For each field we want to fuzz, we need to include a payload. In both cases, we'll use the same word list, but we need wfuzz to only iterate through the files once, sending the first values of both files on the first request, the second values on the second request, and so on. We can control how wfuzz combines payloads by specifying an iterator. We'll run wfuzz and set -w tables.txt twice, followed by -m zip to specify a zip iterator. Since the request requires authentication, we'll set -b followed by our JSession ID value, which we can find in Burp Suite. We'll use the -d argument to send a post request with an empty post body. And finally, specify our URL. Since the URL includes semicolons, we'll enclose it in double quotes. wfuzz sent 6 requests and the application responded to all of them with an HTTP 302. We'll need to refresh the admin page in our browser to verify which payload worked. Excellent. Our payload with subscriptions worked. We were able to correctly fuzz for a table name and verify the database executes stacked queries. In the next section, we'll use stacked queries and the information we've gathered to obtain remote code execution. Exploit SQL injection for RCE. When we are assessing a web application and successfully exploit a vulnerability, it is often useful to take a step back and think about what information we found during enumeration and how it applies to the vulnerability. In our case, we can execute stacked queries through SQL injection attacks. The application.properties file contains some additional information that we will find useful. Based on the file, the application may be connecting to the database as the SA user. The SA user in SQL Server is typically the system administrator account and has elevated permissions on the server, including the ability to change configuration settings. Most importantly to us, if our SQL injection payloads are executed under the SA user, we should be able to enable and use XP command shell. First, we need a payload that enables advanced options. We can use Microsoft's documentation as the basis of our payload. We'll need to encode spaces and then send the payload in repeater. The server responds with an HTTP 302. The SQL statement to enable advanced options doesn't typically result in any output. Since the server didn't return an error, we can assume our command was successful. Next, we'll enable XP command shell. Again, Microsoft's documentation provides the basis of our payload. Once again, we'll encode the spaces and send the payload. Next, we will call XP command shell and verify the database enabled it. We could query the database to determine if XP command shell is enabled and insert the results into the subscriptions table. However, we'll use an easier approach. Let's call XP command shell and execute a curl request back to our host. We'll start a netcat listener at port 8000. Now that our listener is running, we'll update our SQL injection payload to call curl with XP command shell and pass in our Kali's IP address and the port of our listener. Here's our SQL injection payload. We'll need to encode the spaces before we send the payload. Unlike our previous payloads, the application does not respond to our request. However, if we check our listener, we did receive the curl request. Excellent. We have confirmed remote code execution on the server through the database. Our next step will be obtaining a full shell on the server. Obtaining a shell. Now that we're able to execute commands on the server, let's work on getting a reverse shell. Windows Server usually won't have netcat installed. While Kali Linux includes a Windows binary version of netcat, Windows Defender will easily identify and remove it if we try to upload it to the server. While there are ways to modify binaries to bypass antivirus detection, those techniques go beyond the scope of this course. Instead, let's focus on what is available on the server. Since the application is Java-based, we should be able to run a Java reverse shell. We can find several examples of Java reverse shells online. Many examples are written for Linux and therefore target bash or sh to run commands. Since we're targeting Windows, we'll need to run command.exe in our shell. We'll use one from payload all the things as the starting point of our Windows targeting Java reverse shell. However, this shell is incomplete, so we'll need to write some code to finish it. Let's start with the basic shell and review the code. Line 1 declares a string variable for the host that the shell will connect back to. Line 2 defines the port number to connect back to. We'll need to update these values to match our IP address and the listener port we intend to use. Line 3 declares which command we want to run. Since we're targeting Windows, we will leave this value as is. Line 4 contains several lines of code concatenated together. In Java, semicolons mark where an instruction ends. We can have several instructions on one line if the semicolons are in the correct positions. The instructions on line 4 create a process object by running command.exe. Next, they create a socket connecting to the host and port values. The input and output streams from the command.exe process are then sent over this socket, essentially allowing the remote listener to issue commands and get the output. We'll need to wrap this code in a proper Java class. We can use a Hello World example to get the right syntax. Oracle's Java tutorials include a perfect example. The first line declares a class named Hello World App. In Java, the class name must match the file name. The first line ends with a left curly brace. A set of curly braces mark a section of code, also known as scope in Java. Sets of braces can be nested within each other. The compiler will close the braces in the order they are opened. In other words, the curly braces on lines 1 and 5 match each other, creating the scope of the Hello World app class. And the curly braces on lines 2 and 4 match, creating the scope of the main method, which resides within the scope of the Hello World app class. Typically, we indent each section of code one level deeper than the surrounding scope. The main method is an entry point for a Java program. If we were to run the Hello World app, main would automatically run and the instructions on line 3 would be executed. In this example, the program would print out the text Hello World, then exit since there are no more instructions. Since our class name has to match our file name, let's create a file named revshell.java. Next, we'll add the basic class structure based on the Hello World app example, but we'll change the class name to match our file name. We should note that our class name matches our file name, but we exclude the file suffix. Next, we need to add some import statements. Import statements notify the compiler we want to use external classes that are not defined in our code. If we tried to compile or run our Java reverse shell without importing the necessary classes, we'd receive an error. We'll add the following import statements at the start of the file before the line with class revshell. Next, we'll place the example reverse shell within the main method. We'll need to update the IP address value in the host variable. Our code is missing one last piece. If we tried to compile it, we would receive several errors. We received several compiler errors regarding exceptions that must be caught or declared to be thrown. When an error occurs in a Java program, the runtime creates an exception object. There are many different types of exceptions, such as the I/O exception. Each exception includes information about what caused the error. Programmers can handle exceptions in line with a try and catch block, or they can be thrown up one level of scope, back to the code that called the method that caused the error. When a method throws an exception, the original calling code must handle or throw the exception. If a program throws an exception but does not handle it, the program will crash. In our case, we can add throws exception to our main method. If our shell crashes, we can always run it again. Now that we have our reverse shell, we need to get it on the remote server. Let's use a Python HTTP server to host the file, and then use our SQL injection payload to download the file with curl and write it to a known location. Next, we can use a second payload to run the file. Let's start by running Python 3 with -m http.server to run the HTTP server module and then specify our port. Since we used port 8000 in our curl command earlier, we'll reuse that value. Next, we'll update our SQL injection payload in Burp Suite Repeater to download revshell.java. We'll need to write it to a directory that the database software can access. Most systems have temp directories that are world writable. We'll try to write to the temp directory using the temp system variable. Let's paste our payload in Repeater, encode the spaces and %signs, then click Send. Because the server responded with an HTTP 302, our payload seems to have worked. Let's check our Python HTTP server to verify. Excellent! The server downloaded our reverse shell file. Let's stop our Python server with Ctrl+C. Now we need to compile and run our shell file on the remote server. Java 11 and newer versions can run single Java files without having to explicitly compile them in advance. We don't know the version of Java running on the server, but let's try running the Java command to compile and run our reverse shell. First, however, we'll need to start a listener to handle the reverse shell. Now that we have a listener running, let's update our SQL injection payload to run our reverse shell. Let's paste our payload in Repeater, encode the spaces and %signs, and click Send. The server does not immediately respond to our request. However, if we check our netcat listener, we have received the reverse shell. Excellent! Our attack worked and we now have a reverse shell on the machine. We can find the proof.txt file in the working directory of the reverse shell. We can submit this value on the labs page to gain credit for completing the remote code execution portion of this challenge machine.